name is Amir-Kian Kashani-Poor. I'm a string theorist at the Ecole Normale Supérieure in Paris.
Hi, Amir. Thanks for finding time to talk to me today. I know you're very busy right now. You are in the middle of a big event at the IHP, the Institut Henri Poincaré, a quarter focused on the mathematics of string theory. Could you tell us a little bit about this quarter or what's happening?
Sure. So since the beginning, string theory has been fueled by the interaction between mathematicians and physicists. And we felt that the IHP offers this ideal setting to foster this interaction. And so this is these thematic quarters. And so the idea behind the thematic quarter is to have a 3-month period where you invite, in our case, mathematicians and physicists to interact with each other. So the quarter starts off with the School for Graduate Students. That's 1 week in Marseille. Basically where we discuss some of the topics that we'll be covering throughout the quarter. And then throughout the quarter, we have a light program of mini courses and seminars, the idea being to offer a framework to then have topics to discuss between mathematicians and physicists. And then we have several intense periods where we have conferences with many talks a day, where we come up to speed with what our colleagues are working on and hopefully are inspired for our own research.
Okay, excellent. So it's an opportunity to fuel your future interactions.
Absolutely.
So why did you specifically want to offer this opportunity? What is this relationship between string theory and math beyond the fact that physics uses math?
Right. So, physics and math has always gone hand in hand. Not so long ago, physics and math was the same subject. But so with the string theory, which is this theory which is meant to quantize gravity, sort of understand the inner workings of the universe at its very core, that interaction has been taken to another level. We use aspects of mathematics that traditionally weren't thought to be part of sort of the baggage of a physicist. And at the same time, it has turned out that we have something to offer to mathematicians as well. So we use their methods, but we think about things they're doing in a different way. And sometimes our way of thinking about things turns out to be useful to them as well.
That's really interesting. Could you give us an example of one topic that string theorists and mathematicians would approach differently?
Sure. So one reason that math has become such a major part of string theory is because we're thinking about geometry in a new way. So string theory has to satisfy a lot of constraints, and to describe quantum theory of gravity. And it turns out that one of these constraints is that our theory tells us, in some sense, that the world is higher dimensional. So we're used to the world being 3-dimensional. That means that we can basically move in 3 independent directions. And then Einstein told us we should really think about the world as being 4-dimensional, with time being an additional dimension.
Right.
But now string theory says add even more dimensions to that. So like in some models, we should have 10 dimensions. Now that sounds very counterintuitive because, when I want to tell you how to get someplace, I don't have to tell you 9 different positions to move in.
Right, exactly.
So it sounds like that's not really the world we live in. But in fact, it's very natural. It turns out that the 6 additional directions, so remember there was 4 time, and now we have 6 to make up 10,
right.
Are in some sense curled up. They're small, so we can't see them, which sounds like a cop-out. So why say that there's 10 dimensions if you can't see 6 of them?
Right.
But in fact, we can't see them in the sense of, in the same sense as we see the other large 3 dimensions, but they influence the physics in a very important way. So, for example, the particles that we see around us depend sensitively on the geometry of these 6 dimensions. Okay. And now we need the mathematical tools to describe this geometry. So this is really where this interaction with mathematics, or one of the interactions with mathematics, comes in.
Right. Okay. So we can't sense these dimensions, but we sense their impact on the world around us. Right.
That is exactly right.
Okay. So going on.
So and now when in physics, things that we want to compute are interactions between particles, that sort of thing. It turns out that those things depend on the properties of of this geometry. Okay. Now, mathematicians think about geometry just because they like to do that. Okay. And so they'll ask questions. Like they might ask questions. A question, how many curves are there that pass through a point? Okay. So that's a simple question. There's infinitely many curves that pass through a point. And then you can say, well, how many curves pass through 2 points? How many curves pass through 3 points? That sort of question.
Okay.
And so we tell them, oh, that's interesting. That question that you're asking actually has a physical interpretation. Okay. So we can take those numbers that you're getting and fit them together into a function, and that function actually ends up describing interactions between particles. Okay.
Yeah. Wow.
And so for them they'll be like, well, that's interesting, but we don't really care because we're interested in geometry. But then we'll tell them our theories actually tell us that we can calculate that same function in a different way using mathematics, which creates a link between 2 different areas of mathematics. And then they start listening. They're like, well, that's weird. Those 2 aren't really related. We don't believe you. But then we'll do computations in the 2 areas, and we'll say, look, here are the numbers, and they match. And often at times, it'll turn out that those are things that they actually have a hard time computing because they didn't know that this relation exists.
Wow.
So then you have a nice interaction, and you start listening to each other and learning from each other.
Well, that is nice. You're revealing the mysterious underlying connections between things. That's excellent.
Right.
Great. So that's fascinating for you in the field. And then also what I love about these subjects is that even for those of us well outside the field, string theory is captivating. It is mysterious to many people, and yet we're drawn to it. Why do you think that is?
Yeah, I think everybody likes to think about, the big questions. Like, physics in school is fine, right? Like you throw a ball, you can calculate its trajectory. When you think about it, that actually itself is really exciting. But it doesn't really talk to you in the same way as thinking about outer space and thinking about black holes and wormholes and the nature of time and that sort of thing.
Yeah.
Inspires you and sort of gives you food for thought. And so string theory is about that. It's about quantum gravity. So it's about gravity under extreme circumstances. For example, a black hole or the Big Bang. And then I think, if we add to the mix higher dimensions, it gets sort of very, very intricate and sort of exciting, I think.
Exactly. Yes, it is exciting. I agree. Great. Well, enjoy the rest of your time with this group in Paris. And thank you for your time today.
Thank you.
Take care.